In this lecture, I'm going to discuss a method for calculating a value for Euler's number E. To derive this method, I'm going to start with something that seems pretty far away from E. I'm going to start with simple interest. So this is the expression for simple interest. Thinking I'm grabbing the, there we go. That's the expression for simple interest. A is the amount, P is the principal, R is the annual percentage rate in decimal, and T is time in years. You're probably familiar with this. For example, if you were looking at the amount of interest on a loan, let's say you take out a loan for $350, so that would be your principal, and the interest on it is supposed to be 6% a year, so the annual percentage rate is 6%. That means R would be the decimal of that, which would be 0.06, and then T is time in years. So the amount you owe on your loan would be $350 plus, that's the principal, plus the interest, and the interest would be $350 times 0.6, should put a 0 in front of that, times however long you keep the loan, like say 2 years or 3 years. What I'm going to do here is just rearrange that expression by factoring out P. So I have P and then in parentheses 1 plus RT. Now we're going to move to compound interest. When interest is compounded, we usually say it's compounded K, we use the variable K, times a year, then in each of the compounding periods the interest is simple interest. It's just that the principal is changing every time you go into a new compounding period. For example, if you compound 4 times a year, then K would be 4, and every 3 months you would have another compounding period. In that compounding period, the interest is really simple interest. So now I'm going to look at a series of steps, one for each compounding period. So when you start at the first one, of course, well, A0, all you have is the principal. Let's say this is a bank account now. And a bank account is really a loan you make to the bank. So in a sense, it's the same as a loan or bank account. Okay, for the first compounding period, you get the principal plus the interest. So you can write it like that expression for simple interest. But what is the time of that compounding period? It's 1 over K. That's how much of the year has gone by. For example, if you compound 4 times a year, if K is 4, then each compounding period is 1/4 of a year long. If you compound, say K is 2, then each compounding period is half a year long. So in general, T is 1 over K, and that's what this expression right here, that's what we get R over K, because that's the same as R times 1 over K, giving me R over K. Right. Now move to the next compounding period. Okay, at that time, we take the amount here, and interest is paid on that amount. That's why it's compounded. So this amount, and here's the same expression because the interest rate didn't change and the time didn't change. Fine. So what is A1? Well, here's A1. So I substitute for A1 and I get this expression, all this. And you see we've duplicated 1 plus R over K, and so we have this expression here for the second compounding period. P equals P times 1 plus R over K squared. Now you keep doing this, you notice a pattern. Of course, here's A to the 4th. It's P times 1 plus R over K raised to the 4th. So here's how it looks in general. A to the J, if I use the J here, it's P times 1 plus R over K raised to the jth power. Now when J equals K, 1 year has gone by. When J is 2K, 2 years have gone by. So I can write the end of the year amount like this. A equals P times 1 plus R over K raised to the KT. And now the question is, what happens as the number of compounding periods goes to infinity? Right, that's what I'm going in that direction. And this is why E is in there, so I'm going to give you a little heads up if you followed this far and you're probably wondering where are we going with this. Remember that continuously compounded interest had this expression. See the E? That's where we're going. We're getting there. All right. So what we do at this stage is we change variables. We're going to introduce a new variable n, and we're going to say that's k over r. And that's okay because r always has to be greater than 0. In other words, if there's no interest, if there's, annual percentage rate is 0, then really is no problem. So we can write that and substitute that in. So here was the last expression from the previous page. And now, if n is k over r, then k equals n times r. And that's what happened right here. And see, the r over k became 1 over n. And I'm going to use the identity for exponents. Remember, if I had, say, x to this 2 raised to the 5th power, that's the same as x raised to the 2 times 5, the 10th power. So because these are multiplied together, I'm going to break them out. I'm going to put the RT on the outside and the n here, and you can see that that's equivalent, because exponent on exponent, you'd multiply them and you would get the same expression. So I'm just using some algebra here, and now I'm very close to the expression I wrote down here. The principal is right here. So I've got this term, the RT is broken out here, but now I have an expression in the middle that looks a little different. It's 1 plus 1 over n raised to the nth power. Now, as the number of compounding periods goes to infinity, n goes to infinity. And I'm saying that in the limit, as n goes to infinity, 1 plus 1 over n raised to the nth power, that turns into e. And that's what I'm going to show now. First, let's use some more math symbols. I've been using them along in this course. We used them for asymptotes, if you remember, for rational functions. If I want to say n is getting bigger and bigger and going to infinity, instead of writing out n approaches infinity, or what I said, n is getting bigger and bigger and going to infinity, all I have to do is write an arrow. In math, we like to use symbols so we don't have to write so much. All right. So this means as n approaches infinity, that means as n is getting bigger and bigger, I'm saying that this expression in here, which I've broken out here, will turn into Euler's number E. Now, I'm not going to give you a proof of it, and I don't expect a proof on the homework. All I'm doing here is giving you a demonstration. The idea here is this. Euler's number is an irrational number, similar to pi. Okay, how can you calculate pi? The circumference of any circle equals 2 pi r. So I could solve for pi, and pi is the circumference divided by 2r. So if I wanted to find a value for pi, I could just find any old circle, measure its circumference, and divide by twice its radius, and that value will be pi, no matter what the circle is or no matter where I am. Of course, measuring is a little bit difficult, but trying to measure accurately, it's a little difficult, but the end result is that you know a way to calculate pi. How do you calculate E? There's no physical circle or square or whatever that I can grab and calculate a value for E. This is how it's done. It might seem, some work getting to it, but it does work. Also, how does your computer know E? It might know E just because the value is stored in there. It might also use an expression like this to calculate powers of E. Alright, so here is a demonstration, and this is what you do in homework. You make 2 columns. I think that's already set up for you. You put in here, and you put the expression that you're checking over here. You see what I put here? The in I put here, this I put over here. Then what I asked you to do in the homework is, since I said this is turning to E, why don't you put down here a comparison? So I did that. I took the value of E from a calculator, and this is what I wrote down. And now, let n take different values, each one bigger and bigger. So when n is 1, I put 1 into that equation. So that would be, I'll put it right here, 1 plus 1 over n, or 1 over 1, raised to the first power. Well, 1 over 1 is 1, plus 1 is 2, 2 to the first power is 2. That's where I got that number. For the next one, I use 10, so this would be 1 plus 1 over 10, raised to the 10th power. Okay, what's 1 plus 1/10? It's 1 plus 0.1 raised to the 10th power. You're going to have to use your calculator. But when you do, you'll get an answer like this. Now you let n be 100. So I have 1 plus 1 over 100. Where is that? Raised to the 100th power. So evaluate what's in the parentheses, of course. Well, let's see, I'm too close to the edge to write this. So let me try it again a little bit here. So I've got 1 plus 1 over 100 raised to the 100th power. Work out what's in parentheses. Calculator, you can do that on the calculator also. And raise it to the 100th power and see what you get. You get this number. So if you keep using bigger and bigger values of n, you will notice a trend. Again, this is not a proof, it's just something you notice. The numbers get bigger and bigger, but they seem to kind of level off. And you can see how it's getting closer and closer to the value of e. Here's a graph of the situation. Remember, we started when n equals 1. These are values of n. And this, what's graphed over here, what's graphed in the red, is 1 plus 1 over n raised to the nth power. And now graphically you can see the trend. It gets closer and closer. It starts leveling off. It's asymptotically approaching the value of e. Now that expression for e can be used also for powers of e. And this is what is in the homework. So it's presented in the homework. We had 1 plus 1 over n raised to the nth power, and that approached e, but that's e to the 1. And it turns out there is a, see the 1 here and the 1 here? Okay, we can in general write what's shown here. Now we have e to the x, but we have an x here. Alright, and I asked you to demonstrate that for two different values. One, I think it was -3, and the other was 2. Here I'm going to run through the example for 5. So you do just what you did before. You make two columns, and the n goes over here, and the expression that you're checking, that would be this one right here, you put in the second column. In this case, because we're looking for e to the 5th, we replace the x by 5. Then you just pick bigger and bigger numbers of n and see what you get. Here is, whoops, that should be e to the 5th. Here's the value of e to the 5th for comparison, and we see a similar trend. It starts off at 6, which is pretty far away from 148 something, but you see it rises fairly quickly and then seems to asymptotically approach the value for e to the 5th. And here's a graph of the situation. You see it looks very similar to the one for e to the 1st power. In green is the 1 plus 5 over n raised to the nth power, and you see it asymptotically approaching e to the 5th, here's e to the 5th, as n approaches infinity. There are other ways to calculate n, and if you go further in math, then you'll find out some of the others. But this is one example of a method for calculating e. It also gives you practice in considering that how things behave. It's not enough to just know, here's a function, stick some numbers in, here's a function, stick some numbers in. Really what you need to do, or what's best to do, is to look at the trend with the function, not just the value of the function and at some number and say, oh, I got the answer right, which I know if you're short on time, that seems to be sufficient. But what I'd like you to do is look at the trend with these expressions. If you go into engineering, that's exactly what you have to do. You have to look at the trend that the formula is giving you, not just one particular value.